Okay, not sure why a lot of people are missing today, but hopefully more people are going to show up later. Okay, so we're just going to continue talking about these different phases we summarized in the last lecture. So just to give you a brief review, so we have a table for quantum phases. So and the basic idea is we can first divide all, so this is the ground state of all local Hamiltonians. So we can classify them into the short-range entangled state. So short-range entangled state, SRE, and these states all obey the entanglement area law, and they can further be divided into two classes. One is the local order. If they contain just some local order, which means each particle is doing its own, there's really no correlations between them, or very small correlations between them, such as a paramagnetic state. And the other one is called the symmetry-protected topological order, which is something we're going to talk about more today. And the other class are long-range entangled states. So these are the states that cannot be generated from a product state with a finite depth local quantum circuit. And these states could either obey the area law or not. And because we're talking about ground state of local Hamiltonians, even though they violate area law, the violation is actually not huge. It's basically a logarithmic. So basically, it's just going to be a logarithmic divergence. It's not going to be volume law. So if volume law is proportional to the system size, then these are usually the area times the log of the system size. And these systems are basically the gapless critical systems. Basically, if you're at a critical point, or if there's no energy gap, they're basically synonymous, then those states do not obey the area law in general. And then for the area law states, typically these are the gapped ground state, so you have energy gap above the ground state. And these can further be divided into two classes, and we talk about this in more details in the last lecture. So we have spontaneous symmetry breaking states. And these states are only long-range entangled when you observe the symmetry of the Hamiltonian. For example, the transverse field Ising model, if you don't have the field, then the ground state can be in a GHG state if you preserve the symmetry of the Hamiltonian. So that is a long-range entangled state. The GHG state is a long-range entangled. But if you break that symmetry, you can easily just get a state of all the spins in a product state, and that is not long-range entangled. So they're not robust. And then there's a robust version of it, which is the intrinsic topological order. And we briefly described it at the end of the last lecture. So these are the states that no matter what kind of perturbation you add, as long as it's a local perturbation, the ground state is always a long-range entangled state. So you cannot disentangle them into a product state with a finite depth quantum circuit. And one of the example is the this Majorana fermion. So if you have this Kitaev wire Hamiltonian, which is actually obtained by mapping the transverse field Ising model to the fermionic picture, then these Majorana fermion modes cannot actually disappear with local perturbations, and that is actually a long-range entangled state. So that is an example, and we're going to talk more about this in the last week when we introduce the Kitaev torical. So that's another example of intrinsic topological order. So if you have intrinsic topological order, then there's a great interest because these always hold anyons. So as long as you have intrinsic topological order, then the elementary excitations above the ground state, so if you're looking at your first excited state, second excited state, and so on, they're actually non-trivial in the sense that the excitation can be thought as a quasi-particle which is not a boson or a fermion. So for example, in the Majorana fermion case, we know those are actually anyons. They're actually not ordinary fermions. When you swap them together, you actually get a quantum gate, right? So people are actually thinking about using this for doing quantum computing. And for the torical, you also get anyons, but those anyons are not directly useful for quantum computing. So there are two classes of anyons. The Majorana fermions belonging to something called non-abelian anyons, and there are also abelian anyons. Let me see if I spell this correctly. I always forget how to spell the abelian. Yeah, I think it's correct. So it's abelian anyons. So non-abelian anyons basically means if you swap those two particles, you actually get a unitary. And then a binary anyon spacing means you just get a phase. So this unitary is at least 2 by 2 matrix. So it can't be a 1 by 1, otherwise it's just a phase. So that's a difference. So abelian basing means when you swap them, you just get a phase, but this phase may not be 1 or minus 1, because 1 or minus 1 basically correspond to boson and fermions, but if it's anything else than a 0 or pi phase, then it is an anyon. For the Kidari torical, we're going to talk about later, it's kind of weird. They have two different types of anyons, and if you braid any two of them, it looks like a boson, but if you cross-braid the different species, it looks like a fermion. So it's also a abelian anyon, but it's in a different sense. So the phi is either 0 and pi, but it's different for different, choice of the particles. Okay, so these are, the intrinsic topological order. You definitely get much more interesting physics out there, and they can be tremendously useful for storing your quantum information. So there's another thing I want to talk about, which we'll probably talk a little bit more when we talk about this Kidari torical. But there's a very interesting way to think about these two long-range order states. So the spontaneous symmetry breaking, so this one is actually already useful in classical physics. So if you think about spontaneous symmetry breaking, of course, the GHZ state is going to be quantum entangled. But once you have perturbation, in the classical world, it's always going to go to one of the two ferromagnetic ground states, either all the spins pointing in one direction or the opposite direction, right? So suppose your ferromagnetic interaction is in the x, then it's always going to be all spins in x or all spins in negative x. And this type of spontaneous symmetry breaking is already used in applications for information storage. For example, these traditional hard disks, not the solid state ones, just the old ones with a magnetic disk here, and they are basically using spontaneous symmetry breaking there. So each of those small magnetic domains, they basically store information as either 0 and 1, depending on whether the spins in that domain is, aligned in one direction versus the other. And because they're using ferromagnetic material, so that means the spins will always be in the ferromagnetic phase. And you can basically just use a tiny little bit of current, which kind of acts as a perturbation to guide the spin alignment into either, one direction or the opposite one. So that's basically how you, store information into that hard drive. And why are we doing this? And this is actually going to give you an error correction, or it's a self-error correcting code. So the spontaneous symmetry breaking, you can actually think about it as a classical self-error correcting code. Self-error correcting code. And the important thing is it's very good because the code distance is actually proportional to the system size n here. I'll explain what the code distance actually means. So we know the hard drive, even the traditional ones, they can store information pretty reliably, right? You're not going to lose information at least for even several tens of years. And the reason for that is all the atoms, all the little magnets, the electron spins in that little domain, that unit you store information, they're all polarized in the same direction. So it's actually very hard to make an error. If you want to basically change your information from 0 to 1, you have to flip the spins of all the atoms, right? Because they're all aligned. And if you just flip one of them, it's actually fine. So what the code distance means in error correction code basically means that you have how many spins you have to flip, or how many individual bits you have to flip in order to cause the logical bit to be wrong. The logical bit is basically the 0 and 1 we're talking about, right? But the individual spin direction of the atoms, that's the individual bit, right? So you have to have all of them wrong in order to make the whole information incorrect. But of course, that's not easy to happen. Any kind of local perturbation is not going to cause that, right? You have to put like a really strong magnet, on top of your hard drive to actually cause that kind of error to occur. So it's basically a self-correcting error. It's basically a self-correcting classical error correction code with code distance n. So it's actually pretty useful for classical information storage. So we use that. Of course, there's no quantum thing here because it's a classical state, right? You can't store a superposition state. That doesn't make sense. You could get a GHZ state, but that's very unrobust, right? A little bit of perturbation is going to kill that superposition. So you will never have all the spins pointing to the right with some superposition of all the spins pointing to the left. Okay, so then thinking about this intrinsic topological order, phase, then it's actually just a quantum version of that. So suppose we really have a quantum information, we have a qubit, you want to store some information, which is alpha 0 plus beta 1. So how do you do that in some sort of a self-error correcting way? In the sense that if just one of the bits behaves wrong, it doesn't actually affect the logical qubit. So basically, this whole information you are stored in, and you actually need something much more than spontaneous symmetry breaking. You need intrinsic topological order. So Majorana fermion is a very good example, right? So these two Majorana fermions, they actually can store one bit of quantum information. You can store some alpha 0 plus beta 1 there. And you can't actually destroy that information with any local perturbation. So all those qubit between those two edge spins, you can add perturbations to it. It's fine. It's not going to touch that information. And we talked about one of the reasons is, you have these, so the degeneracy of these two qubit states, the 0 and 1 states, they're basically exponentially small. And it's going to be exponentially small under any local perturbation. So you can't actually decohere that qubit. So this is actually a quantum error correcting code, quantum self-error correcting code. With code distance n. So it may not be exactly n depending on the details, but it's basically the code distance is proportional to n. So that means the error has to apply globally on n qubits to flip the logical qubit. Question?
So the classicals corresponding to spontaneous and quantums?
Yeah, quantum is intrinsic. Yeah, that's right. Yeah. So this is also something in that textbook I recommended. So I think it's a really interesting insight. You can really think about these two as classical and quantum error correcting code. Yeah, and I use the word self-error correcting code. It's just in the sense that you actually don't need to do any active. Sometimes this is also called passive error correcting code. It means the same thing. So you just don't need to do quantum gates to correct the errors. You don't need to do anything. The information is just automatically protected under local perturbations. So if you just have some local errors, it's fine. Yeah, question, Paul.
What does code distance mean?
So code distance basically means how many physical bits or qubits you have to flip or do an error in order to destroy, in order to get actually an error on the logical qubit, right? And the larger the code distance is, the better it is, right? And if the code distance is basically almost the same as the number of qubit you use, that's the best, right? So that's the largest code distance you can possibly get. Okay, so of course, there's this big question of whether we should do passive error correction or active error correction, right? So that's kind of a big debate for doing quantum computing. At this point, we don't know. Both of this, is difficult. You need a lot of physical qubit to encode even one error-corrected logical qubit. But I think in some sense, they are somewhat equivalent. You either have to do a lot of complicated error-correcting circuit, quantum gates, or you have to detect the error syndrome to correct the error, or you have to do this very complicated, interacting Hamiltonian, and then you get this intrinsic topological order to do it. Yeah, question, Paul.
Do you have a sense or perspective on the number of physical qubits?
Yeah, so that's a good question. It kind of depends on how much you want your error, you want your qubit to be protected, right? So if you want to get like really, really high, fidelity, then you probably need, something like 1 million qubit physical qubit to get one logical qubit. So it could be hugely, there could be a huge cost to this. If you don't want that good error, fidelity, maybe you can deal with like maybe a few hundred or a few thousand physical qubit and use that as a logical qubit. So I think right now, people working in quantum error correction can just barely achieve something called the break even, which basically means you use a number of qubits. Usually they only use like 10 or 20 because we don't have a lot of qubits at this point. Use like 20 or 20 qubits to actually encode a logical qubit, an error corrected qubit, and they're not using these topological code. So it's just like an ordinary error correction code, such as majority vote, which is the simplest one, right? You just basically have n qubits. If more than half of them is in 1, then you call it 1. Otherwise, you call it 0. But that's, of course, a very naive code. There are a little bit better codes, but they're not the topological error correcting code. So there are codes built upon these Kitaev toric code and others, though they're kind of similar to these topological, intrinsic topological order. So you get better scaling of the error rate with the number of qubits. The more naive ones, at least you can get it working for a few tenths of qubit. But at that point, we can only show that the logical qubit has less error than the physical qubit. So that's called break even, right? Because the problem is if you stack a lot of physical qubit, it's not necessarily going to make you a better logical qubit because each of the physical qubit have error rate in it, and it could actually make things worse at the end, right? So to achieve the break even is already a milestone, and I think that was achieved a couple years ago. I think now people can definitely get some logical qubit which behaves better than the physical qubit. But in order to push the error rate all the way down to 10 to the minus 15, like in the classical computer, we still have a long way to go. And I think people believe if you really want 10 to the minus 15 error rate, you probably have to go through either one of these. Either need to do a topological error correction code actively or passively in order to get that small, because you need some exponential scale. Yep, question?
When companies advertise how many qubits they have in their machines, are those physical?
They're always physical qubit. So if they want to make logical qubit, they will only get one logical qubit, or maybe two at most. And then they're not significantly better than the physical ones. To get significantly better, you need hundreds, thousands, or even millions of physical qubit to encode a logical qubit. Yeah. So this is why we are still in the NISQ era. So there's still noise. We're not in the fault tolerant. If you can get to this, it's basically fault tolerant, right? Because this, when the code distance is n, what it means is the error rate should scale exponentially down with n. So you can easily get to 10 to the minus 15 if you want. If you have a large enough system size, getting to that exponentially small error is actually doable. And that's what we call fault tolerant. But we're not, apparently we're not there. Okay, so all right. So the last thing I want to talk about in this table is basically this symmetry protected topological order. So they're definitely not that useful for quantum information because they actually don't have anyons. So the short way is, even though this is also called topological order, it's kind of like a weaker form of topological order. So you will not get anyons from it. So they can be used for quantum computing, but that doesn't mean that they're not useful. They are still tremendously useful in material science. And one of the things is called, topological insulator. And I'm going to show you a video just in a moment. But for now, let's just try to understand the basics of what the symmetry protected topological order actually means. So I actually gave, I briefly mentioned this when we are talking about this spin 1 anti-ferromagnetic Heisenberg chain, and I showed this lecture, Nobel Prize lecture by Haldane. So this is one of his, big contribution. For example, we look at this spin 1 anti-ferromagnetic Heisenberg chain. So the Hamiltonian is pretty simple. You have nearest neighbor anti-ferromagnetic interaction, and these are spin 1 particles. And what you find is that the ground state and the first excited state has an energy gap. So that is not very surprising. We basically just have a gapped ground state. We're not at a critical point. But what is interesting is that the ground state actually does not have any kind of order. So in this case, when you are in this symmetry protected topological order, then there's basically no local order at all. There's also no, correlations. So the correlations should also decay exponentially with distance. Basically, the spins are not correlated. So this means it's going to be different from either the local order case, where, for example, in the paramagnetic order, all the spins are polarized in some direction. And in this SPD order, there's no such thing. If you measure the spin angular momentum, it's going to be 0 in any direction. Of course, when you do individual measurement, it's going to be either, it's going to give you some non-zero value. But as long as you repeat your measurement and get your expectation value of your spin angular momentum, it's actually going to be 0, for any direction. And if you measure correlations, it's also going to decay exponentially. So basically that it contains no conventional order. So the local order means something like a paramagnetic order, and spontaneous symmetry breaking means that it's like a ferromagnetic order, right? All the spins are aligned in some direction of their interaction, but it's neither one of those. But it's also not intrinsic topological order in the sense that we don't have anyons. And these states are also short-range entangled, which means we can basically disentangle the states with a finite depth quantum circuit. So we have to basically call them a separate name. So this is something that's different from all the other 3 categories we talk about. And they're also gapped, so it's not gapless. They do satisfy area law. So this is the last class we're going to talk about. So this state is kind of a bit weird. They don't have any local order or any the spins are not correlated. And so what exactly is it? So what's actually going on is these systems usually have some interesting edge state. So you can have some edge excitations there. And those edges are kind of similar to the Majorana fermions, but not exactly. So if you think about the edge states there, they're also exponentially localized. And those edges, edge excitations don't talk to the bulk. So in some sense, if you do any perturbations in the bulk, it's not going to lift this edge state degeneracy. So you will also get these exponentially degenerate edge excitations. So usually when you are in this state, you will have a ground state, and then you will have like degenerate edge state. So I'm just going to use a dash line here. You're going to get a bunch of them. It could be either 2 or 4, depending on the symmetry. But this gap here, and also the gap in between of these states, is something that is exponentially small in the system size. So we'll get something like this. So you'll get exponentially, small excitations on the edges only. And if you look at the difference of these states above the ground state, they're actually pretty much the same as the ground state, except at the edge. So this is the reason why the coupling is very small. And it's, in some sense, it's very similar to the Majorana fermion in the sense that the Hamiltonian, you have like a boundary term, which looks like something like an exponentially small coupling with some S1 dot Sn, something like this. It's not exactly like that, but roughly speaking, when you solve the ground state and look at the low energy subspace, you have an effective Hamiltonian that looks like this. So you have an exponentially small coupling between the edge states, which will basically give you these degenerate lowest excited states. So you might think, could this actually be useful to store quantum information? This is great, right? Because when you have this exponentially small degeneracy that are preserved by local perturbations, you can always store information there, right? If the qubit energy difference is literally 0, then it's not going to decohere, right? But there's a problem here. So this is the reason why it's called symmetry protected topological order. So all this is based on the fact that we have a certain symmetry. This is only true, so this exponentially small degeneracy is only true if we obey the symmetry. So in fact, there's a pretty easy way you can lift this degeneracy. You can just apply epsilon of SZ, SIZ. You can either apply it on the edge or apply it uniformly across the channel. So if you just apply a magnetic field along any direction, that's going to break the symmetry of the Hamiltonian, of this Hamiltonian, right? Because this Hamiltonian has SU2 symmetry, but when you apply the sigma z, it breaks the symmetry. And once you break the symmetry, this edge state degeneracy will just be lifted. And the simple reason is, if you look at the spins near the end, if you apply a magnetic field, you're just going to create, energy difference of epsilon, which is a finite value, because that's a Zeeman splitting. So that means it's actually not that robust. It's only robust if you don't have symmetry breaking perturbations. Of course, in reality, there's always symmetry breaking perturbations because the noise in the environment doesn't really distinguish much about your symmetry. So they're definitely still interesting, but not that useful. So this is in 1D. We have this Haldane chain example. But in 2D, things get more interesting. In 2D and 3D, so we have these topological insulators. And the symmetry there is actually protected by something called time reversal symmetry. So as long as you have time reversal symmetry, you're also going to have this edge state. And this edge state in the 2D is kind of like you can flow a current through the edge. And there's an important application there because this edge state basically has a linear spectrum, which means it doesn't have any dispersion. So you can actually get a very efficient current. So it's kind of like a metallic edge state, and then it's an insulator in the bulk. So you can actually use that to build some classical electronic devices. So it's called spintronic devices. So those have very low dissipation. So basically, you don't have any dissipation there. It's not superconducting. You still have resistance, but you don't have heat generation. So you can actually build this with much lower energy cost for if you want to build electronics elements out of this. Of course, the key question is whether this time reversal symmetry can be broken, and indeed it can be, but it's you can actually make it almost not broken. So most of the perturbations in a real material will going to obey this time reversal symmetry, but there's one exception. So time reversal symmetry can be broken simply by a magnetic field. So a magnetic field, because of this right-handedness, you can actually break time reversal symmetry. One way to think about it is a magnetic field vector is something called a polar vector, and that is always going to be different when you do a time reversal symmetry. So as long as you don't have magnetic impurities in the material, the topological insulator is indeed topological in the sense that these edge states are topologically protected. So any local perturbations on the bulk that obeys the time reversal symmetry is not going to break it. Of course, there are a lot of experiments on topological insulators already. It's an extremely hot field a few years ago. And unfortunately, all the real materials, you will always have a little bit of magnetic impurities in there. So they're not exactly protected, but they're close. And people are really thinking about building all kinds of applications out of this. So one other application is these topological insulators are actually very good thermal, what is it called? It's called thermoelectric materials. So if you use it, for example, use it as a fridge, then it's the best material to build a fridge. Okay, so I'm going to show you a video. It's actually a TED talk. So this is actually from the person that invented topological insulators, is Jim Mealy. So he's a professor from Penn State. So let me unmute this. So it's actually unmuted. Okay, I just need to switch here. Okay.
Topological insulators. That's certainly an odd combination of words. I have to say that after having worked in this field for a number of years, I still find it kind of jarring, almost alarming, to see those two words lined up against each other in the same sentence. So one of my tasks today is to tell you what a topological insulator is, how they were discovered, and where it is they may be leading us. The prediction of topological insulators grew out of some work here at Penn, as was just mentioned, with my longtime Penn colleague, Charlie Kane, and was recognized this year with the Breakthrough Prize in Fundamental Physics. But truth be told, the basic ideas behind the subject way predate our own work on it. They have a very long history, and I want to actually tell you about some of that history because it'll let you appreciate what these things actually are and why they might be useful. So if the word topological insulators is hard to look at, let me do a more palatable one. Our graphics department has put this together. I think it very beautifully captures the subject. The graphic in the center, Mind the Gap, is taken from the London Tube, and it's been overlaid on a graph from one of our early research papers on the subject. And that's also an unlikely combination, but really it works. The key to understanding a topological insulator is to pay attention to the warning on the Mind the Gap sign. So I know that this conference is an invitation to think big, and to start, I think the biggest think that I can lead you toward is to give you a summary of the entire subject, not just of topological insulators, but of all of physics. That sounds like a daunting task, but in fact, the heavy lifting has already been done for us. So let me just point you to this graphic which beautifully summarizes this. Okay. This is by Dominic Walleman, who's a trained physicist and also quite a skilled graphic artist. And he lays this out in the style of one of these like beautiful historical tapestries. Far to the left there, we've got Newton, laws of motion. We've got Maxwell, laws of electrodynamics. And then historically, this is followed in the middle of the tapestry by the great revolutions of the 20th century. Relativity, which changes our concepts of space and time, and quantum physics, which is the laws of very small things on very small length scales. An important statement to make is that in a century that saw that kind of revolutionary thinking, perhaps the most impactful for us is actually this thing shown in the lower left. It's condensed matter physics. Condensed matter physics, broadly speaking, one of its primary tasks is to take the understanding from quantum physics and apply it to have a deep understanding of materials and how you can build them and use them for practical purposes. For example, the outgrowth of this discipline is what enables the action of your computers, of your cell phones. It probably ran the GPS that brought you here today and the laser scanner that got you in the door. Okay. And that kind of connection of quantum physics with real-world applications is sometimes called the first quantum revolution. The idea of topological insulators belongs in this sector, but it's part of the second quantum revolution. It's finding new materials that can do these kinds of things more efficiently and perhaps lead us to new designs we haven't yet imagined. So I've been asked a lot to describe topological insulators over the last few years. In the many interviews and discussions that I've had, I find the same questions are always coming up. Let me just walk you through the questions. First of all, what is a topological insulator? Or the variant, what could be topological about insulators? Okay. Or, more broadly, what is topology? Okay. Or, as Mark Zuckerberg put it to us at a laureate's lunch last fall, he asked the question, what is an insulator? Now, likely unknown to Mark, quite possibly, what he was asking is a very deep and profound question. That is the question. In fact, that question, I will tell you, does not have an answer that is both simple and correct. And so what I'm going to do is to back off from that a little bit and talk first about the easier question to handle, which is what is topology? So what is topology? Well, according to the Wikipedia, it's a branch of mathematics. It involves properties of space that are preserved under smooth deformations, things like stretching, bending, twisting, and crumpling. You can't tear and you can't glue. That's interesting in its own right, but it's not going to be allowed for the purposes of this talk. I'll explain this by way of example. So in math, an example would be, you take a sphere, you could squash it smoothly, make it into a disk. Those two are the same. You can smoothly deform one into the other, but you can't smoothly deform the disk into the loop-shaped object on the right. That involves tearing it open and re-gluing it, and so that's not allowed. This is a very general and generic idea. It occurs in mathematics, but it also occurs in many other environments. For example, it could occur in nutrition. Okay. So in nutrition, you would say that by this thinking, an orange could be smoothly deformed into a cookie, modulo the transmogrification of the sugars and so forth. But there's no amount of changing ingredients that'll turn the cookie into a donut. That's not allowed because you really have to poke a hole in it. So what I usually like to point out is that if you have children in the house, make sure they don't learn too much mathematics, because they will try to convince you that the middle panel is the same as the left, okay? And they would be right, okay? So with that input, let's now turn to Mark's question. What is an insulator? And again, I'll start by doing it by way of example. So here's just like a classic experiment. You take a battery, a light bulb, some wires, a nail on one side, a pencil on the other. When you wire this up, the light bulb lights on the left, and what happens on the right is that nothing happens. So the current goes through the conductor on the left, and not the insulator on the right. Okay. So that gives a possible answer to Zuckerberg's question. What is an insulator? You might say the answer is an insulator is not a conductor. Okay. So sadly, that is not a definition, because I learned early on you don't define a thing in terms of what it is not. But sadder still, it reflects a fundamental prejudice, which I would say was the law of the land until about 10 years ago. The prejudice is that the things that are useful are conductors. If you want to transmit energy, signals, information, conductors are the important things, and insulators will ultimately play a secondary role. And that is a universal idea that has a long history, in fact, a long history in this university. It goes back, for example, to the work of Benjamin Franklin on just this subject. He studied it and realized in his treatise that one had to distinguish between conductive and insulating states of matter. And he describes it in this passage that I won't read to you, but I'll tell you that he calls conductors non-electrics and he calls insulators electrics. And he reaches the same conclusion, that the interesting thing is the non-electric. Those are the things that are useful if you want to move what he's calling here the electrical fire. Yeah, this same idea appears in the modern first quantum revolution formulation of this problem. And I'll tell you a little bit about how it works. This goes back to work in the mid-60s by Walter Kohn. One thing you need to appreciate is that in quantum mechanics, electrons, they're waves. And the energy of the wave depends on how much you squeeze it. The more you squeeze, the energy can change quite a lot. That's shown by that curve going up steeply on the left. But the important thing is that even when you don't squeeze it at all, when you sort of make it spread out, what will happen is that there's still a residual energy in the problem. And roughly speaking, that energy is the energy it takes to dislodge electrons from the atoms to get them move freely as waves in a material. The cartoon to keep in your head is something like this over on the right. There are electrons that are bound in orbits on the atoms. You kick them with a little bit of energy, and then they move throughout the crystal. You need to have that energy to remove them, and that kind of situation is called a nearsighted behavior. Electrons bound on any one of those sites know nothing about remote potentials, boundaries. It all doesn't matter. They only know where they are. Until about 10 years ago, that was the law of the land. We felt that that was the universal defining characteristic of the insulating state. So the answer to Zuckerberg would be that in the insulating state, you don't really have anything going on. It's completely inert. The postmodern thinking says that actually misses something important. Okay? We're now in the 21st century. What we now realize is that insulators of that sort actually have a kind of internal DNA. They know something about the medium in which they have been embedded, and that is actually characterized in terms of topological invariance. So we're now in a position to connect these two disconnected ideas. What is topological about insulators? Okay. Well, it's in this DNA. Okay. Here's the refined definition. Insulators are topologically equivalent if they can be smoothly deformed into each other, and they're topologically distinct if they cannot. Okay.
Just to stop here, this is kind of closely related to what we said about this modern definition of quantum phases. If you can sort of smoothly connect these two phases, what we said is a finite depth local quantum circuit, but you can also say it's just connected by some sort of local Hamiltonian. So that's a smooth change. If you can smoothly connect them, they belong to the same phase, and here they say they belong to the same insulator, or you're in the same insulating phase.
So that admits the possibility that these things are not inert. There are actually different kinds of them, different species of insulator, and one has to take careful track of this. Let's describe how this works in a graph. Okay. So here's the squeezing to the right, the energy changing as a function of the squeeze. If you look very closely to the origin there, you see the curve on the right. Now, the steepness of those curves gives you the velocity of the propagation of the wave, the walking man, to the right on the right, to the left on the left. That is the grossest of gross understatements. Okay? A better statement would be something like that. The motion is extremely rapid. You know how rapid? It's roughly 1/100th of the speed of light. That's the intrinsic speed in one of these things. A better graphic would be to have the men disappear altogether. Okay, so they're here now and gone in a moment. But a thing to realize is that there's places on the curve where there's no slope, there's no steepness, and that corresponds to what I'll call the standing man, the standing state. Now here's the key concept. A standing state, a standing man, is not, in quantum mechanics, a man with no motion. Okay, that's the important idea. Okay, the standing state is actually, waves do what waves do. They run through each other, they superpose. The standing state is actually a combination of the forward and backward moving states of the system. This is the only equation that will appear in the talk, and so I'll just walk you through it for how to read it. What you say is that when you have the standing state, the chance of moving forward is the square of the coefficient that precedes it. 1/√2 squared is 1/2. Chance 1/2 moving forward. The chance of moving backward is 1/√2 squared, 1/2. But there's two ways of getting a number that will square to 1/2. They differ by a sign. There are two different ways to superpose the states. They correspond to two really different insulating states that cannot possibly smoothly be deformed into each other. To understand them, you need to pay attention to the London tube warning and mind the gap. The gap contains the DNA. It's the signature of how you have different insulating states. One more graph to see how that works. Here's these two insulating states. In one case, we have a positive parameter there. In one case, negative. Here are the labels, positive, negative, positive. You'll see that you can't possibly take the thing on the left and turn it into the thing on the right, because a number that is positive taken to a number that is negative will somewhere go through 0. And if it goes through 0, that happens. There is no gap. It's actually a conductor. Not only a conductor, there's no place where it's flat. That means there's never any turning around in that state. You can't get the particles to turn around in the special state in between two different insulating states. Okay? It's either all forward or all backward and no turning around. So there are three fundamental ideas. Two, in this case two, in some cases many different insulating states. Boundaries between them are always conducting, and they always have this special no turning around property. That makes this a hugely useful idea. To see why, okay, I'll just point out that in an ordinary conductor, turning around generates a little bit of heat. Okay, now, for example, that's a fact. If you run the current through the nail, it heats up. If you have your laptop running on your lap, it's not only a laptop computer, it's a lap warmer. Okay, there's heat being generated. But if you don't turn things around, there's no, or at least much less heat. Okay. So what's the velocity in an ordinary conductor? Let me sort of bring up a graphic again from the tube to describe this. This was taken last December during one of the many tube strikes, and this is a picture of one of the station stops on one of the lines that was actually running. And you see lots of people. The people are metaphors for electrons, and in fact their motion is limited by their collisions with other people. It's very slow. In a current carrying state in a typical conductor, what's the typical velocity? of the charges, I'll move my finger across the room at the typical velocity. So from the back of the room, at the back of the room, you can't see that. In the front of the room, you couldn't see it either. Okay, it's a very, very slow velocity limited by collisions. That's the situation in an ordinary current-carrying conductor. Now imagine replacing that by this, okay? That's the tube when it's working, okay? One-way motion, very efficient, no turning around, except at the places where you want it, okay? Like at the station stops. So does that actually happen? Yes. If it can, where can I find it? Well, as it turns out, it's not particularly rare. We now know the recipe for looking for these kinds of things, and there are many, many examples of this kind of thing in nature. In the theme of this conference and connecting disconnected concepts, I would say in this case you have many situations where you have materials that are insulating on the interior and conductors on the boundary, and a third and the boundary conductor is special. When you do that, you don't turn charges around and don't dissipate much energy. There's many examples, I'll just flash two. We predicted this for two-dimensional graphene back in 2005. Actually, the details of this have been observed quite recently, published just last month. But in the intervening time, we found that this is possible in many, many three-dimensional crystals. The data on the left there actually shows an experimental verification of the crossing of those two states, the band closure exactly at the boundary with a no turning around rule. So the field has developed rapidly over the last 14 years or so. In the early days, we sort of had the field to ourselves. It was an interesting but a quiet time by any reasonable measure. And these days, we're being overwhelmed by the bounty from the many people who are exploring this and other opportunities to exploit these ideas. So where will this lead us? Well, let me bring up another element. It is not hard to point to situations in our daily life that are being thoroughly penetrated by the output of the first quantum revolution. Computers, cell phones, efficient lighting and LEDs, digital cameras, those kinds of things. I should point out that every one of those devices involves charge motion in the slow mode. We're now talking about replacing that by very efficient transport of charge. So I think one can imagine that. More optimistically, you might imagine really a whole new generation of materials based on these new systems. So where will this lead? I don't really know for sure, but I can give a bit of advice. The advice is keep calm and mind the gap. Thank you.
Okay, any questions? Okay, yeah, so the take-home message here is this topological insulators are basically insulating in the bulk, but on the edges, you actually get a metallic, basically it's a conducting state. And you can actually conduct electricity with very low dissipation because the charge is only moving one way. So I think this is definitely going to open up some very interesting applications, and there are already people looking at them, but I still think it's in early stage. One of the challenges is these things, these edge states are only robust under this time reversal symmetry, which is not mentioned in this talk, but in reality, there are always symmetry breaking perturbations. So they're not exactly ideal. So you still have dissipations because of these magnetic impurities, but I still think they're going to be way better than the traditional bulk conductors. Okay, so that's so much for the application of symmetry protected topological order. It is still important for different reasons. And it possibly could lead to more near-term applications than quantum computing, I think. And we're also going to talk more about the mathematical formulation of symmetry protected topological order in our next topic, which we're going to start today. So for these matrix product states, those can perfectly represent a symmetry protected topological order just in 1D. Okay, so that's pretty much everything we want to talk about with regard to entanglement and how it's related to quantum antibody physics. So today we're going to start a new topic. I think this is our second last topic. So this is for matrix product states and tensor network states. And we're going to talk about this today and also next week. And our last topic will be on this intrinsic topological order. We use Kitav-Torre code as an example. So that will be the combination of this course and also probably the hardest topic. And today we're going to talk about matrix product state. And these are basically a very powerful ansatz for any one-dimensional quantum states. So you can pretty much represent any one-dimensional quantum state in a very efficient way. So you actually don't need exponential number of parameters. You only need a polynomial number of parameters to get a very good approximation of most physical quantum states in one dimension. And there are two-dimensional generalizations, which is called tensor network states, which is still very powerful, but much less useful in calculations because it's very hard to calculate any physical observables from the tensor network state. But still, it is probably the best tool to, for example, to understand quantum states in two dimensions. And Google actually has a dedicated team try to model their two-dimensional quantum computing chip with already 50 or 100 qubits with tensor network state. But we're going to start with something simpler, which is one dimension. And in this case, we already have existing software packages to deal with it. And I'm actually going to show you one example, one software which is actually developed here at Mainz. It's actually a very easy to use software. And there's actually a problem in homework 6. But as I said, homework 6 is optional. I still recommend you to go through it. Okay, so all right, so let's first talk about the definition of matrix product state. So this is also typically just called MPS, so the abbreviation. So what is a matrix product state? I briefly introduced that back in chapter 1. So the idea is that for any many-body state, we can always expand it in the qubit basis or the standard spin basis. So this S here is going to be a vector. So the S here is going to stand for S1, S2, all the way to Sn, where these are basically, you can think about that for qubit, it's just either 0 and 1. If you have a spin S particle, then this can take value from minus S to plus S. So it's just a quantum number. It's a local that labels the basis states for each qubit, for each particle. And then the key question is we want to express this precise S. So there are exponentially many coefficients here, and this is what we call the many-body wave function. In general, this is going to be a 2 to the n by 1 vector, right? So if you have n qubits. But we can think about an ansatz, which is much more efficient. So let's try to represent this as the trace of A1, S1, A2, S2, all the way to AN, SN. So each of this, we call this AI, SI, is a matrix. So this matrix is labeled by two numbers. So the lower label I just labels the qubit, right? So I goes here from 1 to n. So basically for each qubit, you're going to assign a matrix to it. But there's also an upper index there. I call it SI. It's not the matrix to the power of SI. So it's just an index. I put it in the top just to make the notation a little bit nicer. So it's another label for the matrix. So for different SI, for example, for qubit, SI can be either equal to 0 and 1. That means basically you're going to associate each qubit with two matrices instead of one. So for each qubit, you're going to define two matrices. I call it AI0 and AI1. So that SI in particular is just denoting whether the qubit is in 0 or 1. So the SI is directly attached to the SI you have in the wave function. And then you basically just do a matrix product. So you have a bunch of matrices, you have to do a matrix product. Of course, when you are doing the matrix product, the dimensions have to match. So for simplicity, we're just going to assume that these matrices have the same dimension. In practice, they can have different dimension, but the neighboring ones have to match, right? So that's how you do matrix multiplication. So let's just assume these matrices are of dimension chi by chi. So these are square matrices, all of the same dimension chi. So you can just multiply these matrices together. Of course, when you multiply them together, you also get a matrix at the end, which is chi by chi. And then you take the trace of it, which is just summing over its diagonal elements, you get a number. So this is going to be a complex number. And that is basically your wave function coefficient. So that's the precise. So that's your many-body wave function.
What is chi again?
So chi is the dimension of these matrices. It's just the dimension of these matrices. It also has a name we're going to use later on. It's called the bound dimension. And the reason why it's called bound dimension is you can actually write this as a little bit of a diagram. So you can basically write it like this. And each of this is basically going to be your matrix. So each of this little box, so this is going to be my A1, this is my A2, and this is my A3, and dot, 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 right? And then we also have this S, and S people here basically use another leg here. So this is my S1, this is my S2, all the way to, Sn. Right, so when you are doing matrix multiplication, you can think about that. You are basically doing some sort of contraction horizontally, because this is how you do matrix multiplication. You basically sum over the repeated index, right? So suppose you have multiplication of a1 times a2. So what you do is you sum over a1 of, say, I of k and a2 of k and j, and then you sum over k, right? So this is how you do matrix multiplication in linear algebra. This is the ith row k's column, this is the kth row j's column, and then you sum over k. So when you do that, you basically calculate the matrix product. So this is going to be the element you get for the ith row and j's column of the product of those two matrices. So in this sense, this is kind of like this leg k I was talking about. So there should be another leg I here. And then this will be your leg j. But since a2 is multiplied by a3, then these two legs actually will be summed together. So whenever I draw a connecting line, it's basically that you're summing over some repeated index, like the index k. Right. And you can think about each matrix A here, AI here, containing two legs. So these are basically its row and column indices, right? So you can basically call this, for example, this is your K, this is your J. And you also have a separate index, which is given by SI. So which is why I use the upper row here. So this is basically your SI. So each of the AI, it's actually, you can think about it as a rank 3 tensor. So it has 3 indices, K, J, which are the row and column of the matrix, as well as the index SI. So this SI typically is called the physical index, because the reason why it's called physical is because it depends on the state you are looking at, the basis state. So it depends on SI, which is the physical state you are in, right? So if you are in that state SI, then what is the wave function coefficient? And that is related to this lag here, the index SI here. And of course, when you fix the S, these are just standard matrices, and you do a matrix multiplication. This is why it's called a matrix product state. Okay, so the next question is, why do we want to use this? So the first thing we notice is that this is going to be a much more efficient way to represent the wave function, because if you count how many parameters here, there's actually only a polynomial number of parameters in these matrices. So I said that each matrix is of dimension chi by chi. So each matrix will have at most chi square non-zero matrix, chi-square, independent variables, right? And how many matrices we have? So we have n of them, but we also have the number corresponding to how many s we have. So if you have qubits, it's just 2. Are you okay?
I'm okay.
Okay, good. All right, so the number of matrices we have for n qubits, just to be simple, is only 2n times chi-square. So you only have 2n such matrices. For each qubit, you have 2 matrices for the 0 and 1 basis state, and then you have 2n of them. Each one is chi-square. So this is only polynomially scaling with n, right? So that is a lot better than the original wave function where you have 2 to the n different numbers, different independent parameters. Of course, the way you argue is you wouldn't expect a much smaller number of parameters to encode, in general, any state, right? Because if you have a random state, which indeed contains 2 to the n independent variables, there's no way you can write it in this way. But at least you hope that this is a good approximation. And the other powerful thing about this matrix product state is there's this bound dimension chi here, which is a matrix dimension. You can actually change freely to give you more representational power. So in principle, this can actually represent any state, even a random state in the Hilbert space, if you choose your chi to be large enough. For example, if your chi already scales as 2 to the n, then you also have exponential number of parameters in your matrix product state. So in principle, this can actually represent any state. Question, Richard?
So it says n qubits, but what is the value of 2 to the n chi-squared again?
It's 2 times n, it's not 2 to the n. So the reason is that each matrix has chi-square numbers, and then you have 2 times n of such matrices, which is why you have 2n chi-square total parameters in this matrix product state. And the point that you can scale chi arbitrarily to make it possible to represent any physical state. If chi is exponentially large, then you can also represent any state you want. Okay, of course, the hope is that you don't need to use an exponentially large chi. So hopefully these matrices are actually small, and you can still approximate most physical quantum state. And because you can see that this picture, we're actually thinking about the qubits that are lying in an array. So this is kind of natural for one dimension. Question, Kobe?
I think I might be a little confused here. So I, K, and J are the dimensions of the matrices, right?
Oh, IK is just a label.
Oh, just a label.
Yeah, so it's just a label. So what I mean here is that, so for example, this K and J here is just a label, and this runs from 1 to chi, right? It's like a label. Think about a matrix, right? You always have like an AKJ, and the K and J just ranges from 1 to all the way to the dimension of the matrix.
Okay. I thought that
Right.
was just dimensions for the matrix product.
This is just a lag. This is just to show you a schematic way of representing this matrices. And when you are doing the matrix multiplication, you are really kind of just connecting the legs and sum that over. So that's what the matrix product is for. But the dimension is just denoted by chi.
Right.
So and they're all square matrices. Dimension is just chi. Yeah. And there are 2n chi square parameters in this whole matrix product state. Okay. So, and it turns out that most one-dimensional quantum states can be efficiently represented by this machinery. And in the simplest case, let's consider the case of chi equals to 1. So the bound dimension is actually equal to 1. So in this case, the wave function per psi s here is just represented by numbers, because each of this is a number, right? If the matrix dimension is 1, this is just a number. And because we're doing a multiplication of numbers, the trace is also not necessary, because the trace of the number, a 1 by 1 matrix, is just equal to itself. So in this case, per psi is just given by A1, S1, A2, S2, all the way to AN, SN. So each of this is basically just a complex number. Right. In this case, you basically just get Qn complex numbers. Okay, so that is your many-body wave function. And here I have a quick question for you. So in this case, if I'm just using a matrix product state with bound dimension 1, then do you think I can represent an entangled state? So can I represent an entangled state? So A for yes, B for no, C, I don't know. Okay, so you can think about this. So in this case, the many-body wave function is just a product of numbers, and there's actually two complex numbers because the upper index SI can be either 0 and 1. So can we actually represent an entangled state for this n-qubit system in this way? Yes or no? Okay, I think this is a simple enough question. Most of you have already voted, and I think it's pretty clear that the answer is no. So you can't actually encode an entangled state in this case, because if you look at it, so there are a couple ways to look at it. First, you can see this wave function actually takes a product of numbers, and what you can actually do is this per psi is going to be a tensor product of per psi 1, tensor product per psi 2, all the way to per psi n, where each of the per psi I is going to be given by ai of 0 plus ai of 1 of 1. Right, so then you are doing a product. So you can plug this in, and then you do a product, then you can see the coefficient is exactly given by A1 of either 0 and 1 and A2 of either 0 and 1. So it's always a product of those numbers. And the other way to think about it is this state is only parameterized by 2n complex numbers instead of 2 to the n. And the only case you only get 2 times n complex numbers to parameterize the state is where you have this product state, because each qubit is given by 2 complex numbers, and then you have n qubits, so you are just using 2 times n complex numbers. So it's literally a product state. So with a bound dimension 1, you can only represent a product state. Question, Colin?
So when you write out the state up there, are those cats implied to be there?
Oh, this is just a coefficient, right? So the way we write this precise is just a coefficient. So you have the expand with the basis, right? And here I'm using the cat notation. So if I don't use the cat notation, it's just a coefficient. All right, so so that's the chi equals to 1 case. So it's trivial. It's not that interesting. And then things starts to get interesting when the chi goes to 2. So if you just have a bound dimension of 2, you can already represent entangled state. And I can give you a very good example, which is the GHZ state. And we talk about this a couple of times. This is a pretty simple but important entangled state for n qubit. We just have all the qubit in 0 plus all the qubit in 1. By the way, for homework 5, problem 1, you're asked to calculate the entanglement entropy for this state. Homework 5 should be relatively easy. I'll give some hints next Monday, but you should first try to think about the problems yourself. Okay, so this is a GHZ state, and this is definitely a many-body entangled state, right? It's not a product state. And it turns out that you can just use a chi equals to 2 matrix product state to exactly represent it. And you need to be a little bit more creative in thinking about what matrices you want to use. I'm going to actually write it down. So for each AI of 0, independent of the qubit, they're all going to have the same matrix because this state is kind of symmetric, right? So if you swap any 2 qubit, it's the same state. So this state is not distinguishing each qubit. So we're actually going just need 2 matrices. So this AI of 0 is going to be equal to 1, 0, 0, 0. And then we have AI of 1, that is 0, 0, 0, 1. So let's see why this is the case. So as we said, the many-body wave function is given by, so let's write the state. So per psi is given by sum over S, and then you have a trace of A1, S1, A2, S2, all the way to AN, SN, and then we have the basis states S1, S2, all the way to Sn. Right. So we want to show that this big summation here with these 2 matrices is actually going to collapse to that GHZ state. And it's actually not that hard to show it. So first, let's look at the case where the S1, S2 are all equal to 0. So in this case, you are really just multiplying this matrix n times, right? So all the AI A1, AI SI is AI of 0 is equal to this. So when you multiply this matrix here n times, it's going to give you the same matrix. It's not hard to do this calculation. It's a diagonal matrix of 1, 0, 0, 0. It's going to give you the same matrix, and when you take the trace of that matrix, it's going to give you 1. Right? So in this case, the per psi S is equal to 1. And for the similar reason, if you set all these S to 1, then you're basically just multiplying this matrix n times. And then that, again, is going to the same matrix. So the trace of this is also 1. So these 2 are also 1. So there definitely has to be a normalization coefficient. We're going to talk about that later. But then, if you look at any other case, you're actually always going to get 0. So if you're looking at any other S combinations without all the qubit to be in 0 or 1, then you're always going to multiply, for example, one of these, each of these 2 matrices together. And if you see that, if you multiply the 1, 0, 0, 0 with 0, 0, 0, 1, it always gives you 0, right? Because these are diagonal matrices. You just multiply the diagonal matrix element, and that is always 0. So whenever you have at least one of the 2, 2 of the different matrices appearing in the same time in the product, it's always going to give you 0. So this is perfect because in the GHZ state, we only have 2 basis states with non-zero coefficient. And all the other ones actually give you 0. Right? Okay, so that is pretty much correct. So this does represent that. The only thing that's not is the 1 over square root of 2 factor. But there's an easy fix to it. We can just rescale this, this matrix a little bit. So we're going to rescale this matrix by just 1 over square root of 2. But this one will be to the 1 over n's power. And similarly for this, we're going to rescale this to 1 over n's power. So if you multiply n of them together, it exactly give you a 1 over square root of 2. So that's just a constant factor. It shouldn't be a big deal. Okay. So this is a simple example showing that a bound dimension 2 MPS can already represent some very interesting many-body entangled state. Of course, in this case, it's not that useful because the GHZ state, is already simple enough, right? Why do we even bother writing it using these matrices? But the key idea is that for more complicated entangled state, the matrix product state can give you a much more compact representation than actually using 2 to the n different coefficient. And it's not only representing the state, you can also do calculations on these states much more efficiently. Okay, so the next one is to give you a more non-trivial example, which is the one we're going to talk about in more details. It's called the AKLT state. So this one actually will directly explain to you what exactly is that symmetry-protected topological order. And if you remember, in Haldane's Nobel Prize lecture, he also mentioned about this state. So this AKOT actually stands for a physicist name. So this is Afnak, Kennedy, Lieb, and Tasaki. So the most famous physicist here is Lieb. So he's a professor at Princeton, and he actually did a lot of important work in condensed matter physics in the last century. I think there's kind of like only 5 completely rigorous general theories in condensed matter physics, and Lieb contributed to 3 of them. So he's a pretty famous theoretical physicist of our age. Okay, so what these 4 physicists predict is a very interesting state. At that time, so this is actually back in 1987, the matrix product state is not invented until around 2005, so it's relatively recent. So they don't actually know anything about matrix product state, but they actually, their work is trying to find some kind of analytically solvable Hamiltonian that is closely related to this Haldane's conjecture, basically this spin 1 antiferromagnetic Heisenberg model. So we just talked about this today. So Haldane conjectured that the ground state of this should have some very interesting properties that people haven't discovered. It's basically belonging to the SPT phase. People later know. But the AKOT, these 4 physicists is trying to find a Hamiltonian that is close to this, but we can find the ground state analytically. So we don't know the analytical ground state of this Hamiltonian, this antiferromagnetic model. So this one is pretty hard, but they're trying to find something easier. Okay, so how do they do it? What they are basically considering is a pretty intuitive state. So just look at the picture on the left here. What they are basically envisioning is, so let's start with a bunch of qubits. In this case, we need 2 n qubits. So we have, so the label here goes to n. So, but we're basically going to have 2 n qubits, right? So here is basically given by these dots. And then we're going to pair the qubits here, like the 2nd and the 3rd, the 4th and the 5th, and so on, into singlets. So each of this line here is just a singlet. So it's basically 1 over square root 2, up, down, minus, down, up. So we talked about this singlet before. It's actually going to be the ground state of just the Heisenberg interaction. So if you have S1 dot S2 with a positive sign, the antiferromagnetic version, the singlet state minimizes that energy. But of course, you can't minimize all of them if you have a chain of them. But here it's fine because I'm only pairing these 2 and these 2. So it's basically a product state of these singlet pairs. So this is a simple state. It's a product state of 2 n qubits. The only exception is these 2 edge ones, they're not paired. So I'll actually only have n minus 1 pairs instead of n pairs. So for 2 n qubits, I'll have these 2 red qubits being isolated. So they're just in the product state with the others. There can be any 2 states. And later on, we're going to show that it's these 2 free spin 1/2s that are going to give you these edge states we talked about. Those are also related to the edge state in the topological insulator. It's just a more complicated 2-dimensional version. Okay, so of course, if you just have 2 n qubits in this state, it's not interesting, and we can write the wave function pretty easily. It's just a product of these singlets. And the next thing is going to be much more non-trivial. So we're actually going to project these 2 qubits. Look at this. It's actually the ones that are not paired, but paired with the others. So we're going to look at these 2, and we're going to project these 2 qubits or spin 1/2s onto a spin 1. So that's what we're going to do. So this looks a bit weird, but let's try to think about it. So if you have 2 qubits or 2 spin 1/2s, the Hilbert space dimension is going to be 4, right? You can have up, 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 down, down, up, and down, down. You can also use the singlet triplet basis, right? So you can have the singlet state. You can have this 3 triplet states, right? So these are also 4 states. It's just a different way of different choice of the basis for a 2-qubit Hilbert space. But if you think about a spin 1 particle, it only has 3 basis states, right? Because the spin 1, if you look at the spin angular momentum in any direction, you can have either 1, 0, or minus 1. So the spin 1 basis states are actually represented by the plus, which means the angular momentum takes the value of plus h bar. For 0, angular momentum is 0. Minus angular momentum is minus h bar. So those are the 3 angular momentum basis states. So that spans the Hilbert space of a spin 1. So apparently, you're going to miss one state, right? So so how do you map the 4-dimensional Hilbert space to 3? And you have to drop one. And then what you are dropping is basically that these 2 qubits are in spin 0, right? Because if you add 2 spin 1/2 particle, you can either end up in a spin 0 or you end up in a spin 1. the spin 0 will give you a Hilbert space dimension of 1 because it's just one state. That's the singular state. And the spin 1 will give you 3 triplet states. So you're going to drop that. So this is why it's a projection. If you think about a projection, it's going from a higher dimensional space to a lower dimensional space. So you are doing a projection here. And this projection operator is explicitly written here. Right? So you can see that we have 3 basis states for the spin, for the 2 spin 1 halves, the up, this, and this. So these are the 3 triplet states. But we're lacking one term, which is the singular state. So that one is projected out. So that means if the spin is actually, if these 2 spins is actually in this singular state, it's going to be projected out by this operator. So this operator applying on this state will literally give you 0 because this state, the singular state, is orthogonal to these 3 triplet states. Right? So it's going to be projected out. But if these 2 spins are actually in one of these 3 states, it's going to be mapped to the spin 1 eigenstate, either the plus or the 0 and the minus. And you basically just map it according to the spin angular momentum. So this is pretty much synonymous. If you have 2 spin 1 halves in this triplet state, we just label it as the spin 1 state with a spin total angular momentum pointing up. So that's a mapping. So you're going to do a projection for these two spins, and make sure that they're not in the singular state. They can only be in a triplet state. So that's a projection we're doing. So it is this projection that makes things really interesting because you see that these spins are entangled in this way, and you're trying to project these 2, right? So that's an interesting thing. If you instead you're trying to draw a circle here and do that projection, it's going to be trivial because you're always in the singlet. If you project out, if you project this component out, you're just going to get 0, right? So the interesting thing is projecting these 2. So then you will get some weird things going on. And in general, if you do this projection, for example, on a computer, you're going to get a state that is very complicated. And it actually contains 2 to the n different non-zero coefficients. So in the standard qubit basis, you'll get a really complicated wave function with a lot of coefficients. And there's no easy way you can simplify that many-body wave function. And this is the case where the matrix product state actually becomes useful. So you can find a very simple matrix product state that represents exactly the ground state of this, basically after that projection, basically representing this state. So this is called the AKOT state, and we'll talk about the parent Hamiltonian later. So what Hamiltonian's ground state actually exactly give you this state. But I want to briefly mention that this idea can actually be generalized to 2 dimension as well. And that generalization to two dimension is a lot more interesting. The 1 dimension is pretty much like a tutorial now. It's going to be in the textbook. But the 2-dimensional ones, there's a lot of active research going on. So first, the generalization of 2 dimension is actually relatively simple. So what you're doing here is that, so first you prepare a lot of qubits. In this case, I think it's 4n qubits instead of 2n. So each lattice side you have 4 qubits. And you're still doing these singlet pairs for the neighboring ones. Right? So this is a more complicated lattice geometry. You have a hexagon lattice. And again, for each lattice side, you're going to put 3 qubits. Right? And then you're going to draw a line for to the neighboring ones, to the neighboring side. All these lines denote a singlet pair. And then what is more interesting is we're now going to do projections. For the square lattice, we're going to project all these 4 qubits into basically a spin 2. So in this, in the 1D case, it's spin 1. But here we have 4 spin 1/2 particles. So we always want to project to the largest possible spin subspace. So 4 spin 1/2, they can add up to spin 2. So you're going to project these to the spin 2 subspace, and these 4 to the spin 2 subspace. So you keep doing this, and then you're going to get a very non-trivial state. And similarly for this, so you're going to project these 3 to a spin 3/2 subspace. So you keep doing these projections, and you end up with some complicated state. But these states are actually quite useful. The name of this is called projected entangled pair state. I think it's also called PEP state. So it's called projected entangled pair state, just from the way it's defined. And these states, first, they can actually be represented by a generalization of the matrix product state, which is called the tensor network state. And the other thing is, this is going to actually be able to represent all the intrinsic topological order state. So for 2 dimension, if you generalize this to 2 dimension, you can actually represent this intrinsic topological order state, like these toric code. And this has become a very important tool for dealing with 2-dimensional quantum matter, including those two-dimensional quantum error correction code. All right, so we're going to stop here, and next class we're going to talk more on the AKOT Hamiltonian and how it's represented by the matrix product state. All right, okay, I'll see you next week.